This diagram shows the emission spectra of hydrogen. When excited, hydrogen gas doesn't emit a continuous rainbow of light, but rather distinct, isolated frequencies. Classical physics offered no mechanism to explain these sharp, discontinuous lines. In 1913, Niels Bohr proposed a radical fix. He suggested that an electron orbiting a nucleus could not emit energy continuously. Instead, it could only release or absorb energy when jumping instantly between strictly defined orbital paths. To make his model match the observed hydrogen spectra, Bohr imposed a strict mathematical constraint. He introduced the integer variable n, which artificially restricted the electron's angular momentum, forcing its energy levels to be discrete. The math worked perfectly, but it carried a critical physical flaw. Bohr dictated that energy is quantized, but he provided no physical reason why an electron should behave this way. It was a rule imposed from the outside. As long as physicists treated the electron as a classical, point-like particle moving along a fixed planetary trajectory, the actual physical cause of this quantization would remain hidden. The first step toward a physical explanation came from Louis de Broglie, who proposed that the electron is not a solid point mass at all, but a wave. This section details the equation for the dual nature of matter. It directly ties momentum, a property of discrete particles, inversely to wavelength, a property of continuous waves. Under this physical reality, the Bohr orbit ceases to be a track that a particle runs along. It becomes a continuous standing wave that must perfectly close in on itself around the nucleus to avoid destructive interference. But this introduced a massive structural problem. If matter behaves as a wave, its movement through varying potential fields cannot be calculated using Newton's laws of motion. To predict how matter waves behave, physicists had to discard classical trajectories entirely. They needed a completely new mathematical framework. Erwin Schrödinger constructed that new framework, developing the foundational equation that governs the propagation of matter waves. This block presents the Schrödinger wave equation in its most compact form, h hat psi equals E psi. At the center is psi, the wave function. It is the absolute storehouse of information, encoding everything that can be known about a particle's state. But the math only works under rigid boundary constraints. To represent physical reality, the wave function must be well-behaved. It must be single-valued, continuous, finite, and smooth across its bounded space. The state of a system is no longer defined by distinct coordinates like position and velocity. It is a continuous mathematical function that must strictly obey the physical geometry of its environment. Because an electron is a wave distributed across space, you cannot simply measure a single classical property at a specific point. Quantum mechanics solves this by replacing classical observables with mathematical tools called operators. This table maps classical systems to their quantum operators. To find a particle's position or its linear momentum, you must use the specific operator assigned to that property. The most critical operator for determining a system's state is the Hamiltonian, which represents the total kinetic and potential energy of the particle. To extract measurable data, you execute an eigenvalue equation. The operator acts mathematically upon the wave function to pull out the observable property. For example, the Hamiltonian operator performs a second derivative on the wave function. By doing so, it extracts the exact total energy, E, as a scalar eigenvalue, leaving the original wave function intact. With this rigid mathematical machinery in place, physicists could finally test how a particle behaves under physical confinement, without relying on Bohr's arbitrary assumptions. This figure illustrates the particle in a 1D box. It serves as the ultimate proving ground for Schrödinger's wave mechanics. A particle moves freely inside an impassable potential well. The potential energy is zero inside the box, but rises to infinity at the walls. Because the walls are impenetrable, the boundary conditions demand that the wave function must drop exactly to zero at the edges. The wave cannot exist outside the box. When you apply these constraints, the geometry takes over. Waves that don't hit zero exactly at the boundaries are destroyed by interference. Only discrete wavelengths survive. Exactly an integer number of half-wavelengths must fit perfectly inside. This proves what Bohr could only guess. Energy is quantized naturally. It happens because the physical boundaries of confinement permit only specific, stable wave geometries to exist. This equation yields the total energy for the confined particle, derived directly from those surviving wave functions. The variable n in the numerator is no longer an arbitrary rule. It represents those specific physically allowed wave states you see mapped here. This leads to an inescapable theoretical question. What happens to the energy if a particle sits perfectly still, setting the quantum number n to 0? If n equals 0, the wave function flatlines everywhere. The wave vanishes entirely. A confined matter wave with 0 energy simply ceases to exist. This discrete energy level plot shows the consequence. To exist at all, the absolute lowest possible state for the confined particle must be n equals 1. This forces it to hold an inescapable positive energy value. In classical mechanics, a particle in a box can easily have 0 kinetic energy by simply resting motionless on the floor. Quantum mechanics forbids this. Wave mechanics replaced Bohr's guesswork with geometric necessity. Confinement guarantees quantization, and 0-point energy proves that a confined particle is